This is my favorite part. This is so cool. All right, this is how a contraction of a skeletal muscle is going to take place. So how does it start? What is the first thing that must happen if we are going to contract a skeletal muscle? Who's that? Dude, that's somebody really familiar. This is a somatic motor neuron, and it's actually going to be connected to our skeletal muscle. And here's my skeletal muscle. What was this thing that I told you? That's my motor end plate. But this is nothing more than a skeletal muscle cell. So this is the whole thing. What's inside of this, like down here, if I were to draw, you would put all your myofibrils filled with all the myofilaments. You would surround each myofibril with sarcoplasmic reticulum, right? You would have T-tubules squishing down in. This is my sarcolemma, okay? So that's, make sure you're clear on that. This is just a folded piece of sarcolemma. I kind of feel like I want to draw you a T-tubule. This is a T-tubule. I'm going to have it go off into la-la land. But it's just a tubule that comes out, and my cell membrane, my cell continues. Also in here, we might as well draw this while we're doing some myofiber anatomy reminders. Remember that we had the myofibrils, those all with the sarcomeres. They were surrounded, do you remember this, by sarcoplasmic reticulum. So I'm going to draw sarcoplasmic reticulum here. It's like a bubble, but imagine that it's surrounding myofibril in, like, underneath this. I can't draw it because we'd have to, like, peek through it. And then what's all this stuff? Everything that is in here, it's the sarcoplasm. So it's just cytoplasm in here in this other places. Okay, let's do this. I'm ready. The first thing that has to happen, we have to have a somatic motor neuron fire an action potential. So you can imagine, here comes my action potential. And the action potential comes to the axon terminal, and what's going to happen next? You already know. This is all, I mean, this should be like, boom, total review. When the action potential hits the axon terminal, who's going to open? Voltage-gated calcium channels. And who's going to roll in? Calcium. I got to try to make sure that my numbers match. So voltage-gated calcium channels open, and then calcium rushes in. That's my number 3. After calcium rushes in, calcium is going to do what? It's all familiar. Calcium is going to stimulate exocytosis of vesicles that are holding what? Neurotransmitter. And you know this too. Who's the neurotransmitter inside this vesicle? Acetylcholine. So this is acetylcholine, and it's released in the, okay, that's cool. That's number 4. Acetylcholine is released into the synapse. Number 5, acetylcholine, what does it do once it's in here? Doggies. It has to bind to receptors. And which receptors are these? These are nicotinic acetylcholine receptors. So let's just make a note. These are the Nick clowns. And they look like that, nicotinic acetylcholine receptors. So the acetylcholine comes in and binds. Now, we also know what happens when acetylcholine binds to a nicotinic receptor. You know this. Basically, those nicotinic receptors are sodium channels. And when acetylcholine binds to the receptor, it opens, is a sodium channel. So basically, it allows sodium into the cell. Okay, are you cool with that so far? And I believe that is my number 6. So let's review. Action potential triggers calcium to come in, which binds to vesicles of neurotransmitter, which are barfed into the synapse through exocytosis. Acetylcholine is a neurotransmitter. It binds to nicotinic acetylcholine receptors on the motor end plate of our skeletal muscle, sarcolemma, which causes the receptor to open sodium whole channel ways through. Sodium rushes into the skeletal muscle cell. This causes the skeletal muscle to depolarize. We've been cool with action potentials and depolarizing neurons and repolarizing neurons, but we haven't ever talked about any other cells that depolarize. The skeletal muscle cell is doing it. So here comes a wave, a depolar, no, we gotta make it yellow, whatever that, look, just like I did up here. That was an action potential. Here comes an action potential. No, it's not an action potential. Here comes a depolarization wave. And watch what happens. It's going to wave right along through. It's going to travel down the T-tubule. So now it's just hanging out next to the cell membrane, but now it travels down the T-tubule. What number is that? It's number 7 in Wendyland. The depolarization wave, do I call it an action potential? No. It travels down the T-tubule. This is so crazy. Are you ready for this? Now, oh my gosh, now there is a series of proteins that have a really cool setup that basically they're voltage-gated calcium channels. I wonder if I made that number 8. Calcium channels, voltage-gated calcium channels in the sarcoplasmic reticulum, which was this thing right here, open. But who's in there? Well, I forgot to fill in who's in here. Clowns? Calcium. And not just a little calcium either. The sarcoplasmic reticulum is filled with, oh my gosh, wait till you see who it's filled with. This is like the coolest story ever. And it's only a little bit late. Only just a little. Look. Got to find the right color. What? Who's this guy? Doesn't it look like the sodium-potassium pump? It's not. It's a calcium pump. It's an active transporter that uses ATP to pump calcium into the sarcoplasmic reticulum and requires a huge amount of energy, but is super strong and will rip the calcium out of the cytoplasm just to fill the sarcoplasmic reticulum. Because why? Because we just had a depolarization come down. We opened up calcium channels. And where did calcium go? Uh-oh. Calcium comes out. I mean, it's going to like jet down its concentration gradient and get out into the sarcoplasm. That was still number 8. Okay, are you ready to get really crazy now? Calcium. Calcium, we learned already. Somebody has a calcium binding site. Who is it? It's your good buddy troponin. So now I'm going up here. I'm not actually going to draw any of these other pieces for you, I don't think, unless I feel like I can't stand it. Calcium binds with troponin. Troponin was that piece of the thin filament that held tropomyosin in place, which was blocking actin's myosin binding site. Right? How many of you actually pushed pause and played that over again 62,000 times? Okay, so let me see how I organized. We bind with troponin. That's going to move. Oh, look, I wrote it all down for you. Tropomyosin. We're about to contract, folks. So that myosin binding site is revealed. Dun, 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 dun. Now you have myosin binding site free and available. No more tropomyosin hiding the goods. What do you think is going to happen? Well, it's only logical. Myosin binds to actin. Did I say it that way? That the myosin binding site on actin was covered, but now it's revealed, and myosin already had the actin binding site available. Myosin. What state is the myosin in right now? Well, it's ready to rock and roll. It is in cocked format with the little heads ready with their little actin binding sites ready to attach, but also with the ADP plus P ready to go. So that's what all my myosin heads look like. I mean, all my myosin molecules. When myosin binds to actin, that causes a shape change. And you have, like, totally, of course it does, because anytime molecules bind to each other, they change shape. So myosin binds to actin, and the shape change causes it to kick ADP plus P off. So it kicks it off. Peace out, pound. Now ADP plus P is no longer there. What happens to my myosin? The ATP, the ADP plus P, isn't there to hold it into that cocked position. And now the myosin head contracts. And I actually put all of that as part of number 11. That whole thing is 11. Binds to actin, the binding kicks off the ATP, now the myosin head contracts. The whole thing shortens. Now, if ATP binds again, so now you've got your myosin looking like this. All of them did. You got it a little bit shorter. If ATP binds again, awesome. You're just going to recock that head and grab at a different location, which is going to cause, once you can grab, then you're going to cause another contraction. And this happens like over and over and over again. Look, I don't know why I wrote it this way, but 11 to 12 strokes happen about 5 times per second. Why didn't I just say 60 strokes happen every second? Or maybe that's not what, I have no idea what I meant by that, but it happens fast. And they can keep doing it as long as they have the ATP available to recock and as long as calcium is still in the cytoplasm, in the sarcoplasm. Now, this player down here, this little transporter, is ferocious and will rip the calcium off of the myofibrils. So it's not messing around. It's going to remove the calcium unless there's another stimulus from the somatic motor neuron. And we know that the action potentials can be generated like every 0.4 milliseconds or something just outrageous. Maybe it was 4 milliseconds. It wasn't very long. It was a fast turnaround. And so you can have a whole lot of calcium exposure and a whole lot of muscle contraction. Does it kind of make you want to act it out and like do like a performance of that?